I read somewhere that they found a diamond planet. First, is that anecdote true? Yes.
Yes, that planet has an orbital period of less than a day.
That means it goes around its star in less than a day.
In less than a day, there is solar seismology and there is stellar seismology.
Do you use artificial intelligence to help you with these calculations, with this research?
Well, yes.
Hello, Magali Deleuil.
Hello, Christophe.
We are very happy to have you on the set. We'll be able to talk about many things, about exoplanets. We'll also be able to talk about the study of different stars that you have also worked on. So, for those who don't know you, could you introduce yourself a little, summarize what you've worked on in particular?
I'm a professor at Aix-Marseille University. I conduct my research at the Marseille Astrophysics Laboratory. I mentioned that I'm a professor because my work is actually twofold. I teach university students. And then alongside that, I have my research activities that I carry out at the laboratory. So in terms of my career, let's say it's been relatively diverse since I've done, well, if we go back to a very, very distant past. But it's also interesting to see that even in research, you don't have to have a straight line career, I would say. So I started by working on very evolved stars, stars that are almost at the end of their lives. Then I had the chance to meet Alfred Vidal-Magyar, who was working here at the Paris Institute of Astrophysics. And I focused my research on what are called circumstellar disks, which are disks of gas and dust found around stars. In fact, these are interesting environments because these disks actually accompany the formation of stars. And actually, planets will form inside these disks. And maybe it's because I was working on this type of object. Well, the discovery of the first exoplanet was announced, meaning the first confirmed planet around a star other than our sun. And little by little, I shifted towards research more focused on exoplanets.
All right, so you said earlier that you worked on stars at the end of their life, yes. What's interesting about it? How does a star actually die?
So actually a star is, maybe the idea we have of it is that it's a celestial body. I want to say unchanging, but that's completely wrong. A star is born from the contraction of clouds of gas and dust. That means most of the mass will concentrate in the most central region of the star. And what happens is that from a certain point when the mass becomes very large, the temperature and pressure conditions are such that actually the atoms will fuse and form heavier atoms. So we take hydrogen atoms and actually we fuse them and that will form helium atoms. It's a process that will produce energy. It's kind of the opposite of what we see in fission, which is where we take a very heavy atom like uranium and break it into lighter atoms. So that's what we're trying to do at Cadarache with ITER, but we're still having trouble doing that kind of thing. But on the other hand, this process of fusing light atoms into heavier atoms is something that stars do naturally. And so, in fact, the star begins its life as a star at that moment, I would say, a bit more mature in a way, in its most regular phase, which we call the main sequence phase. And that's the phase our sun is in. And our sun, for several billion years, will turn the hydrogen in its core into helium. And this process generates energy that appears on the surface of the star as light. So for a star like ours, visible light, and so on. And so there comes a time when during this process, the reservoir, in a way, of hydrogen atoms runs out. And then there will be a certain readjustment inside the star in order to start fusion reactions. So this time, not from hydrogen atoms anymore, but from helium atoms. And like that, we will produce carbon atoms, oxygen atoms, and so on. Atoms that are heavier and heavier. And in this process of readjustment, the star will go through somewhat violent phases, let's say, where it will readjust its interior in order to increase the pressure and temperature in the central regions to produce these fusion reactions with heavier and heavier atoms. And so, of course, it all depends on the initial mass of the star. So these adjustment phases can be more or less violent. If the star is not very massive, there will be a phase called the planetary nebula phase, where the core contracts, and this is accompanied by the expulsion of part of the star's atmosphere. If the star is more massive, there will be a nova or supernova phase, where there is a very violent ejection of the star's outermost layers. This is a very brief summary, of course, because these adjustment phases can be numerous and more or less violent, actually.
By the way, what determines the different ways a star can die? Because we've seen that there are explosive phases like supernovas. There are phases that are a bit gentler, where they slowly expel their outer layers. What determines whether a star ends one way or another?
Essentially, the determining factor seems to be the mass of the star. The more massive the star is, the faster it will consume its hydrogen and go through all the phases of burning heavier and heavier elements. And it will end up with successive burning layers, for example, to produce carbon from helium. Then we can actually go as far as producing iron. Ultimately, the elements that make us up come from these burning phases of the star as it evolves. So the more massive the star is, the faster its processes are, and the more violent the internal and external adjustments and these explosive phases actually are.
All right, so obviously the star needs to be massive in order to have the ability to fuse elements that are heavy enough.
Absolutely. The more massive it is, the more it will go through burning phases that actually produce very heavy elements like iron, nickel, and things like that.
All right, so as soon as it's heavy enough, it fuses heavier and heavier elements up to iron. Does it fuse elements heavier than iron?
Yes, there are some heavier elements that are produced, but actually in smaller quantities. It's a question of relative abundance, and among the heavy elements, iron is the dominant one.
So then you started analyzing these stars, working on these stars at the end of their lives. Then you said that you worked on stars with disks of matter around them.
Yes, what we call circumstellar disks, that is, if we start with an interstellar cloud made of gas and dust that eventually collapses, most of the mass concentrates at the center and forms the star. And then, because all of this is rotating, actually, let's not forget, the centrifugal forces will stretch the rest of the cloud, actually, or that part, the remaining part of the cloud, into a disk that accompanies the formation of the star, actually.
All right. And it's from this disk that planets can potentially form?
Exactly. So in the disk, actually, which also orbits around the star, there will be settling, meaning the dust will tend to settle in the plane of the disk. And there, collisions happen, not necessarily violent ones. At this stage, but let's say bigger and bigger aggregates of dust particles start to form. So this is very, very simplified, of course. These aggregates will grow in the plane of the disk until they form pebbles, things like that. And then we move on to a phase where the pebbles can also aggregate to form kilometer-sized objects, which we call planetesimals, and which will in turn grow through collisions that can ultimately be non-destructive or not necessarily destructive, and thus form planetary embryos, so bodies of planetary size,
Which,
as a result, through their gravitational influence, will accrete the remaining gas in the disk.
all right, what got you interested in this particular field? So what's interesting about these disks?
Well, it was so maybe I should put things into context a bit since I started working in this field around maybe 93 or 94. So that was before the discovery of the first exoplanet. And at the time, the classes I taught at the university in planetology, well, I taught my students that we actually knew of 9 planets all in all. And these 9 planets were all orbiting around our sun. So, knowing whether planets existed elsewhere around stars other than our sun was a completely open question. We could assume so, because otherwise it would be very anthropocentric to think that in fact we were the only ones in the universe. But there was no other evidence.
All right.
And so when Michel Mayor and Didier Queloz announced the discovery of 51 Peg B, first of all, the article was exceptionally well written, since in fact it explored all the hypotheses that could be made to explain the signal they had measured. And so for each of the hypotheses that were examined, well, in fact, they provided arguments that ruled out the hypothesis, and the only one that remained was the planetary hypothesis.
Okay.
But we really need to put things in context. So, as I was saying, at the time I used to tell my students, we only know 9 planets, all orbiting our sun. And when you look at the characteristics of 51 Peg B compared to the planets in our own solar system, well, it's an object that had absolutely nothing in common, since it had an orbital period of about 4.5 days.
That's fast.
That's very fast compared to Mercury, where the orbital period is around 90 days or so, with a body that had a mass that was about half the mass of Jupiter. So if you remember your planetology classes, in our own solar system, we have 4 so-called terrestrial planets, meaning rocky like Earth, which are all, how should I put it, at a short distance with a short orbital period, since we have, starting from the Sun, Mercury, Venus, Earth, and Mars. So 4 rocky planets. And then after that, 4 completely different planets, gaseous objects, so more fluid in nature than Earth, which are Jupiter, Saturn, Uranus, and Neptune. And they are at a greater orbital distance from the Sun. So actually, it's really not the type of planet we were expecting.
All right. And so is that what gradually sparked your interest in studying planets?
Well, yes, on one hand, it was very, how can I say, it was actually a mini revolution in the field. At the time when Michel Mayor and Didier Queloz published this paper, I mean, the whole community started asking questions. There were other papers that were published, other people, other researchers who even examined their data to try to see if there were any flaws, any mistakes. Exactly, there weren't any. What you need to know is that at the same time, the Americans, who were also searching for planets around nearby stars, a bit like 51 Peg B, analyzed their own data. But at that time, they had excluded signals with short orbital periods, so they went back to their measurements. They searched without limiting themselves in terms of orbital period for massive planets far from their star. And in the process, they published a few new planets that were similar to 51 Peg B. So things moved very quickly from that moment on. And then that's what made me shift a little bit in that direction. So while I was studying circumstellar disks, I was looking, ultimately, I was interested in the environment where planets form, trying to determine the physical properties and the composition of that environment. And then it turns out that my laboratory was involved in the design of a small space mission that was being proposed to our National Space Agency, which is actually the CNES. And so actually there was a researcher from the laboratory who was working on this mission, which was initially a mission to study stars. All right. and it was called choroconvection and rotation. It was a mission that came after another space mission, another instrument, a space telescope, whose launch unfortunately didn't work out, which ended up, I think, in the sea, which was called Ivris. And its goal was to measure the vibrations of stars, because stars are not, as we saw earlier, they evolve, but they also vibrate a bit like the Earth, which has its own, how should I say it? We actually know about seismology on Earth. The Earth isn't a dead celestial body either. It has waves that travel from its interior to the surface. This results in earthquakes, of course, and it's a similar phenomenon in stars. Is there solar tectonics? There is tectonics. There is stellar tectonics. And this is called seismology. So asteroseismology for stars. And so it's interesting to be able to measure these pulsations of stars, because they allow us to infer the internal structure of stars. And let's not forget, stars are, in a way, the basic ingredient of the universe. Even if you study galaxies, you need to understand how stars are made and how they evolve. And so making these astroseismology measurements is important also ultimately to refine stellar models, to understand how stars are made and to trace their evolution. All right. And so at that time, there was this Space Telescope Instrument project that was proposed to CNES, actually by researchers in stellar physics, specifically in Toulouse and Paris, if I remember correctly. And it turns out that there were 3 colleagues from Paris who said, oh, but the instrumental characteristics of this telescope are interesting. And it would allow us to find exoplanets using a different method than the one used by Michel Mayor and Didier Queloz, which was radial velocities. In that case, we could observe transits. So maybe transits, radial velocities, yes, I'd like us to go over that a little bit. If you have a star with a planet, the two are linked by gravity. So the movement of the planet takes place in a plane. Let's say as a first approximation, the star stays in a plane. That's what happens in the solar system. And so the first thing to do is we say that the planet orbits around the star. Actually, that's not true. As soon as you have 2 massive bodies present, both will orbit around the common center of mass. So actually, if we take the case, for example, of our sun with the Earth, let's simplify and just take the planet and the sun, okay? So actually, the common center of mass is slightly shifted compared to the center of mass the star would have if it were alone. If it were alone, it would just spin on its axis and that's it. Here, it rotates on itself, but it will also follow a periodic motion around the common center of mass, which mirrors the planet's motion. Renewed movement of the planet around the common center of mass as well. Également.
Okay.
So actually, if you took the sun with only the Earth and placed yourself outside the solar system, you probably wouldn't see the Earth, but you would see that the sun has an annual motion around a fictitious point, which is the common center of mass, a 365.25-day motion around the center of mass. And the amplitude of this motion is proportional to the mass of our Earth.
Which still results in movements that are already relatively tiny, because when I look at the difference in weight, but also sometimes complex movements, because in a system with only one planet, overall we understand, but if there are 5, 6, 8 planets,
what happens? So, for example, in the case of 51 Pega CB, actually, what Michel Mayor and Didier Queloz saw is exactly that. That is to say, the star 51 Pegasi shows a periodic movement with a period of about 4.5 days and with an amplitude that is compatible with an object of about, now we know it's about half the mass of Jupiter. And so the movement is very periodic. Of course, in the case of the solar system, it's a bit more complex because actually, in addition, the planetary mass in our solar system is mainly dominated by Jupiter and then Saturn. All right, so as a result, the center of mass of the entire solar system is beyond the surface of the sun. The more massive it is, the more the center of mass is shifted compared to the position of the center of mass of the star alone. And so indeed, when you have several planets, you will first see, in a way, the signature of the dominant planet in terms of mass. And then afterwards, you will see variations that are due to the other planets present in the system. But that means your signal will be all the more complex to break down and analyze, of course.
I'm just making a quick side note. So, as a result, these methods are effective for finding planets that are rather large and close to the sun. So, clearly, planets unlike those in our solar system.
So yes, absolutely. That means that no matter which method we use, we have biases, observational biases, right? So because these planets exist, massive planets close to their star, that explains why in the end we managed to detect the first exoplanets. The ones we detected at first were, I want to say, extreme outliers compared to our own solar system, you see. If these planets hadn't existed, maybe today we'd be talking about something else, or you wouldn't have invited me, you see? It's not obvious that exoplanet science would have developed to this point. Because objects like Jupiter, which are quote unquote the easiest to detect, the biggest, the most massive, well, they are. You have to accumulate years of observation because the farther the planets you want to detect are from their star, the more you have to look for periodic motion over years and years. And that actually makes things more complicated, especially when you're searching blindly. All right, so with radial velocity, that's the gravitational effect we're sensitive to. And that's why we measure the mass of the planet. With the discovery of this first confirmed exoplanet 51 Peg-B around a star like our Sun, it completely opened up this field of research. And on top of that, it pushed astronomers, I would say, to really persevere, actually, to accumulate years and years of observation. And now we have the data that allows us to start exploring the range of orbital periods where we expect to find analogs to Jupiter and a bit to Saturn. You see things like that. So, and this is really the discovery that completely transformed the field, which clearly opened a new field of research. As a bit of background, I had participated in a workshop that was specifically about searching for planets outside the solar system. The year was 1995, I think it was at the beginning of summer, and it took place at the Haute-Provence Observatory, where Michel Mayor carried out the observations. And so actually we were examining the different methods that we could implement. And the two typical cases that were used a bit like benchmarks actually were Jupiter and Earth. And so there were different methods that were presented. So the radial velocity method, the transit method, which we'll explain a bit later. There was a radio method, radio detection. That is to say, if you take the solar system, for example, there are what we call magnetic planets, which have a magnetic field like our Earth. They develop what we call a magnetosphere, which is the area where, if you like, the planet's field, the planet's magnetic field dominates and is shaped in a way by the solar wind. Our magnetosphere is all the more important because it protects us from the most intense and harmful solar rays in a way for life. and it deflects the solar wind and so on. And that's why we have polar auroras in those regions. At the Earth's poles, actually, when the energetic solar rays, UV and so on, arrive. During major eruptions, they manage to penetrate into the lower atmosphere of our planet. Because the magnetosphere, at that moment, the magnetic field lines connect to the Earth at the Earth's magnetic pole. And so during strong solar eruptions, etc., we have this aurora phenomenon where the UV and X-ray radiation from the sun ultimately interacts with the atoms, typically on Earth, nitrogen and oxygen, which are present in the Earth's atmosphere, and create these auroras. So all of this, to get back to the other planets in the solar system, the giant planets have huge, enormous magnetospheres. They have a strong magnetic field, and ultimately planets like Jupiter or Saturn are kind of radio sources, since we can observe the magnetosphere at radio wavelengths, which are really significant. And so typically the thing I was thinking about in all the presentations we had about the different methods we could imagine for detecting planets, honestly, I really bet that we would eventually be able to see planets by their radio emissions. So we're waiting for announcements that might come in the months ahead. But actually, the problem with radio is that the universe is not at all, how should I say, silent, if I may say so. There's a strong radio emission, and for now, we still don't have any confirmed radio detection.
And I wonder, isn't the sun itself already a source that tends to overwhelm?
Maybe yes, especially if we want to observe nearby objects, stars. But yes, stars are radio sources too, of course.
Earlier, we talked about several methods to detect planets, and there was still the transit method left. Yes.
So the transit method then, if you've been following, the movement of planets happens in a plane, or the movement of a planet happens in a plane. And if you imagine a star that has a planet, and if the orbital plane of the planet, if I may say so, happens to be close to your line of sight, you will periodically see the planet pass between you and the star. And when it passes in front of the star's disk, the planet, in fact, it doesn't actually emit light, strictly speaking. Because the difference between a star and a planet is that a star, as we saw earlier, is a source of energy since it produces light. Fusion reactions take place in its core, so it produces light, while we mainly see a planet because it reflects the light from its star. The intrinsic difference between a planet and a star is that a planet is not a source of energy, okay? So it comes down to, if you like, seeing when the planet passes in front of its star, the passage of a dark disk in front of a bright disk. And so the planet will block part of the star's light. And so if you continuously measure the light from a star, and when the planet passes in front of the star, you will see a drop in light. A drop in light, and then you get back the star's original light when the planet finally leaves the field of view in front of the star. So that's actually the transit method.
How can we distinguish a planet passing in front of a star from the star's own variability, actually? Because that must cause differences in brightness.
Actually, you don't measure stellar vibrations like that. We aren't able to see that kind of thing. We don't actually resolve the surfaces of stars except in very rare cases. We resolve the surface of the sun, which allows us to extrapolate a bit, and then make the connection using other observables. But even during a transit, we don't resolve the surface of stars either. But to measure the vibrations of stars, what we do is take the integrated light, just like we do for transits, and then we perform a frequency decomposition. All right, there you go. And so we have signal analysis techniques that then allow us to infer the internal structure of stars, actually. But the signatures are completely different. If you want, transit means that you record the light you receive from the star. We continue for months, even years, because don't forget, if you take a planet like Earth, a transit happens once a year, so every 365 days. To be sure it's a transit, ideally you need at least two, which allows you to determine the planet's orbital period. If you really want to be sure, you wait for the third one. Well, after that, we have different tricks that might let us avoid waiting for the third one, but that's ideal. So that means you recorded the light from your star continuously during all that time. That's what we call a light curve. And actually, what we can do with this light curve is perform a frequency analysis on it to try to find the signatures of the star's vibrations.
Okay.
We can also, from this light curve, for example, determine the rotation of the star itself. If it happens to have spots, meaning surface contrast like our sun, which has sunspots, and so we can observe the evolution of these spots over time and also determine the rotation of the star. So in the end, it's actually the same astrophysical signal that's being analyzed qui est analysé in a different way and which provides complementary information.
So in your field of study, did you work on studying these exoplanets or on discovering these exoplanets?
Actually, I did both because after that famous Corot mission, so the way observations, space telescopes, and space missions are carried out. If I may digress, space agencies issue calls for ideas for instruments in a way. So on a more or less variable basis, it depends on the agencies, it depends on the schedules and so on. And scientists respond. The first response is a bit general. There's what's called the science case. What would be the scientific objective of an instrument? And finally, what would this instrument look like in order to answer the scientific question of interest? And so actually that's what happened with Corot. So the colleagues who work in stellar physics had responded to a call for small missions from CNS. And our three Parisian colleagues, who were Alain Léger, Daniel Rouen, and Jean Schneider, sorry for the memory lapse, so they said, but actually, given the instrument design you're proposing for this convection and rotation mission, we can use it to try to find transits of planets outside the solar system. And that was in 96, something like that. And so actually the mission design was revised in order to be able to do both asteroseismology and the search for transits. And the mission theme became convection, rotation, and planetary transits. And so, well, as often happens, the instrument evolved a bit. It was selected and it evolved. We brought in European collaborators. It was launched in December 2006. And so during that whole phase, I was actually working both on the detection of transits and on characterization. What interested us wasn't just detecting for the sake of detecting, but knowing what these planets look like. The transit method, since it's a light effect, we're looking at two disks, right? That means it's a geometric effect. And so it allows us to measure the radius of the planets. The radial velocity method, since it's a gravitational effect, allows us to measure the mass of the planets. So if you manage to combine both transits and radial velocities, you get an estimate of the mass and the radius, and therefore you get an estimate of the average density. You start to know what kind of object you're dealing with. What is the nature of this object? Is it more gaseous, like Jupiter, Saturn, and so on? Or does it have an intermediate density, like an icy object and so on? Or is it rocky?
We can know the mass, but in this case, it's the mass relative to its star. But still, no.
You are absolutely right. Excuse me, I interrupted you. But all the methods often give you a parameter of the planet relative to the same parameter of the star.
But you still need to have the mass of the star to really get an idea of the mass of the planet and therefore its composition. That means we can know the mass of a star.
Absolutely. And it's the same for transits. You must know the star's radius. So actually what we do is so you need the radius, the mass of the star, and to do that we use the same data that we have. It's one of the methods, but that's the way we proceeded, and often that's how we proceed with exoplanets. The radial velocities, you measure them from the spectrum of the star. The spectrum is the light from the star as a function of wavelength. All right? And what this gives you as information is the composition of the star's atmosphere, if you prefer. So which atoms are present in the star's atmosphere? These atoms leave their mark in the light emitted by the star in the form of I'm trying to put it in terms that aren't too obscure. So from atomic transition, actually, these are variations. The electrons, that make up an atom will change their excitation level depending on their interaction with the photons coming from inside the star. And this results in a whole series of, actually, these are bands, I don't know how to say it, of radiation. Yes. You can see it that way. Let's say that the light from the star isn't monotone, but it shows variations that are the signatures of the atoms present in its upper atmosphere.
Okay.
And from the analysis of this spectrum of the star, we will deduce the speed of the star at a given moment. And actually, it's the velocity component of the star along our line of sight, and that's what we call the radial velocity. Hence the name radial velocity method.
All right.
So, to get the mass of the planet, you make a series of spectroscopic observations of the star. For each of your spectra, you measure the velocity of the star along your line of sight, that is the radial velocity, and you end up with a series of radial velocity measurements. You check if your radial velocity measurements show any periodicity, which would indicate that the star has a planet, or at least that you have detected a planet. And if the planet has been observed by transit, you will try to measure its mass. And at the same time, you take the series of spectra you have of your star and you analyze the composition of the star's atmosphere. All right? Because each of the atoms present in the upper atmosphere leaves its light signature. In a way, you analyze that. That allows you to deduce the temperature of the star, its surface gravity, its composition, and all that, compared to models. Then it allows you to deduce the mass and the radius of the star.
Okay. So, very broadly speaking, the light from a star allows us to get a glimpse of the chemistry inside it and therefore to have an idea of its composition and its stage of life. And since we know what color to expect, well, what type of light, what type of radiation we expect to see, knowing the chemistry inside, these shifts compared to what we expect to see allow us to estimate the speed of the star relative to us.
So if you want, we could almost estimate the speed. Well, yes, you still need to know the composition because you have to know the position of the transitions of the atoms present in the upper atmosphere, at rest, actually. But yes, that's what it comes down to. You measure the speed at different moments, and then you do an analysis by comparing the composition, as you said, at a given moment with what you expect from the models.
Okay, so once we have the mass of the star, we can then understand the mass of the different planets that orbit around it.
Absolutely. And you have mass and radii. So you also have the radius of the planet. And that gives you information that is absolutely fundamental about what kind of planet it is ultimately.
I read somewhere that they found a diamond planet. How do we go as far as understanding the composition? First, is that story even true?
Yes, 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 I remember very well. But the colleague who published that article, I worked with him afterwards. Yes, yes, absolutely. So actually, basically, you have an estimate of the average density of your planet. And what we're going to do is we're then going to compare this estimate with models of planets, of planetary interiors. So here as well, it's a bit like with stars, but you're going to make a certain number of assumptions. You're going to assume that your planet, because it has a certain mass and is what's called differentiated like Earth. For Earth, the core itself has 2 layers, if I remember correctly. Then the mantle, the crust, and so on and so forth. So here, given a model of a differentiated planet and some compositions, and you will look at which, among all the possible compositions, would explain your observables, that is, mass and radius.
Okay.
All right, that doesn't mean it's the truth. It's very degenerate. Often we have several possible compositions that can explain just 2 observables. Let's be clear, we can complicate the system a little by taking into account the irradiation from the star. All right, so maybe to clarify things a bit, imagine you have a planet that's very close to its star. If to explain its density, you have to say it must be very rich in water. Your model has to be as realistic as possible, meaning you can't just say, I have an ocean. No, you'll end up with a water vapor atmosphere because your planet will be subjected to significant irradiation. So the water won't stay in liquid form on the surface. It will evaporate. It will form a layer of vapor. Maybe some may remain liquid in the deepest layers, but that's all.
All right, so actually we're looking for a set of clues that allows us to consider different scenarios that are more or less likely.
Exactly. We actually proceed a bit like a detective. So we start from certain observable data and then we try to increase the information we have. We analyze our observable data with models that can be more or less elaborate, of course, and that can involve increasingly complex physics as well. And then we push the observations further. For example, we have the James Webb Telescope, which enables us to start probing the atmospheres, or at least the upper atmosphere, of certain exoplanets in specific configurations. And there we get new information that helps us try to better understand the physics of these objects.
In your career, have there been any planets that you or your colleagues have discovered that have left an impression on you or intrigued you?
Well, yes, I think there are some objects that amused me. All right, maybe objects where the star is very active. I found that really fascinating because we have very turbulent light curves, let's say. All right, all right. Then, well, this might seem strange to you. An object I found quite fascinating is Corot 3b the third, planet discovered by Corot because it made us ask questions. The estimated mass is 21 times the mass of Jupiter.
Of Jupiter?
Of Jupiter. And so with an orbital period, I kind of forgot, but it was less than 10 days, if I remember correctly. But that raised questions. What's interesting is that it brings up questions. Because normally we say that the transition between the smallest stellar object, which is the brown dwarf, where the simplest fusion reactions can start, and planets, actually, we don't really know. But there are theories that say it would be around 13 times the mass of Jupiter. So it was interesting because it called all of that into question a little bit. What is the nature of this object? Is it a brown dwarf, but one that's very close to its star, and it was the first one that close to? And then, on top of that, we had an estimate of the radius. Or is it a brown dwarf? And in that case, it means that the way we distinguish a planet from a very low mass stellar object. That's still an open question. And the other object I found interesting is, of course, Kurosatsube, because that was the first confirmed rocky planet, and that also raised questions. Because there too, we weren't expecting that kind of signal at all, but Kuro was well suited for it. And it was a mission that was designed, an instrument that was made for planets with short orbital periods. And Kurosatsube has an orbital period of less than a day.
That means it orbited its star in less than a day?
In less than a day. So the star is a little smaller than the sun, but still the surface temperature is around 1000 degrees. It's really a very, very, very hostile world. And what was interesting is that, so today we know that it is rocky, etc. But from the discovery stage through to the confirmation and the fact that today I can say it's a planet, it's a rocky planet, it was difficult. It pushed us a little bit to our limits, both for the transit method, and the transits are visible, and also for obtaining the mass. Why? Because the star is very active. It's not a calm star at all. And that causes problems for radial velocity measurements. And for the transits, it was kind of the same. We had problems not with detection, but with the actual analysis of the transit itself, which we need to get an accurate measurement of the planet's radius. That was difficult too. But as a result, it became, I want to say, a good case study. We continue to use it to refine our detection methods and our methods for measuring parameters, what we call characterization, and that's the most interesting part.
By studying exoplanets, have we seen solar systems that are radically different from each other? Has that changed our perception of how a solar system forms, at least a little?
Absolutely. The first exoplanet discovered, 51 Pegasi b, has nothing to do with our solar system. If you take Coro 7b, as I told you, it has an orbital period of less than a day. There too, actually, it's something we absolutely did not expect. And the other interesting thing about Coro 7b is that its radius is, if I remember correctly, about 1.5 times the radius of Earth. And that too is something that planet models did not predict at the time. You have to put it in context. And then Coro was quite a modest instrument, practically at the same time. NASA's big mission called Kepler began operating. And Kepler completely revolutionized the field. Alors, Compared to CORO, it's a much larger telescope that was dedicated to the search for exoplanets and exoplanets similar to Earth. That means it had much better photometric sensitivity than ours. Unfortunately, it didn't detect any confirmed Earth analogues, even though there are some candidates. But on the other hand, it completely revolutionized the field. It revealed planetary systems, systems of small planets packed very tightly together. You can have 3, 4, or 5 planets closer to their star than Mercury is to our Sun. These are rocky planets, what we call super Earths, so rocky planets larger than Earth, like Corot 7b. All right, a bit bigger. And then there are others that have characteristics more like Neptune or Uranus, but again with a very short orbital period.
Does that mean our solar system is more of an exception to the rule? Or is it still more or less the norm for how planetary systems form?
Personally, I'd say what this teaches us is that planetary formation. As we might expect, it's certainly a common phenomenon that accompanies the formation of stars, with more or less success, but it's relatively ordinary. However, to answer precisely whether we are an exception or not, that's still difficult. Today, for the simple reason that we are not yet able to explore that part of parameter space. I mean, if you like mass and orbital period, we remain sensitive, if you like, to small planets close to their star. With a long orbital period, we start to be sensitive to large planets. As I was saying, analogues to Jupiter or Saturn are still difficult to detect. But anything with small masses, really, like Mercury, Mars, okay, and then Venus, Earth with a longer orbital period. Right now, we still don't have the means to really detect them. And that's the goal of the next space mission called Plato, which is scheduled to launch in January 2027, and we'll try to finally address some of the limitations we had with Kepler.
All right, so in 2027, we could potentially get results about exoplanets that are more or less in the same family as our planet.
But we hope maybe not in 2027 because it's, you see...
I mean, that might be optimistic.
There you go. No, but it takes time. We're going to need time. The instrument is complicated because we're dealing with 24 cameras, some of which are looking at the same stars. Now, we're really going to have to understand how the instrument actually works, even though we're preparing for it today. And then, of course, we'll have to observe, analyze the data and all that. But that's really the goal. We want to be able to answer the question, ultimately, how often do planetary systems form that are closer to another one, right? And by having both, if you will, the radii of the planets through the transit method and the masses of the planets. With ground-based observations that will use the radial velocity method, but with the best precision we can hope for, because actually that's what it was. That was Kepler's problem. Kepler observed faint stars. And actually, for the radial velocity method, since we're looking at the spectrum of stars, we need photons, we need bright stars. It works even better when you're dealing with bright stars, especially for small planets, since we're actually looking for a signal that's very faint. And so that's what we're hoping for. And the other advantage of Plato, which I think will be interesting, c'est que cette fois-ci, the stellar analysis is fully integrated with the analysis of the planets. And so we will have the masses of the planets, the masses of the stars, their radii and their ages through astroseismology. And the ages, that's super important. Because in the diversity of planetary systems that we know today and that we've observed so far, we're still not really able to know in the end what is the driving force of evolution that can lead to this diversity. Did the planets form where they are? Did they form farther out? That's what we think. Did they evolve? But in the end, are rocky super-Earths the remnants of an evolutionary process or not? And so for that, we need the ages. And the only way to get ages is to have the stellar age of the system, the age of the system's star, et surtout d'avoir an age determined for as many systems as possible and in a homogeneous and precise way.
To go back a little to our solar systems, we do have a particularity, which is that the first planets are rocky planets and the following planets are gaseous planets. Is it a physical mechanism that causes this, like a centrifuge or a decantation system that would make the lighter elements settle down? Or actually, has the study of exoplanets shown things that are sometimes completely reversed?
Yes, we have things that are completely reversed. We think that actually the gas planets we find close to their star were formed far away from the star. Why? Because actually you need mass to form big planets. All right? So actually what happens in your circumstellar disk, if we go back to that, where the planets are going to form, is that the temperature isn't constant. The closer you are to the star, the hotter the disk will be. We have what's called a gradient, all right? And you have to go far from the star to have temperatures that allow you to keep the light elements. The light elements will tend to disappear more quickly in the hot region because of turbulence, thermal agitation, you know, all right? So we will concentrate the heavy elements near the star and the lighter elements, the gas, etc., far from the star. So what we think is that in principle gas planets like Jupiter form at a great distance from the star, in a place where there are still heavy elements, certainly in the form of ice, right? Which will make up the core, and then the core being becoming at a certain point massive enough to accrete gas. And then there is an interaction between the planet and the gas. Well, the disk, which can lead the planet to, in a way, move toward the innermost regions of the disk, so close to the star.
All right. In our solar system, are the planets stable or can they still move over time?
I would say it's pretty stable, but I'm not an expert in dynamic evolution models. I think what can move are more likely the lighter bodies like asteroids, dwarf planets, especially those on very eccentric orbits, things like that. But in the current planetary configurations, yes, there are certainly some scenarios. For the outermost giant planets, they could still migrate a little bit, but here we're talking about significant time scales over millions of years. And that depends on the models.
Do you use artificial intelligence to help you with these calculations in this research?
So listen, yes. So we can use it in different ways. Yeah. A few years ago, it turned out that I had offered an internship, okay, to a second-year master's student. And I had an engineering school student, among others, who had applied for the project. And then my colleagues and I, we didn't take him. We preferred another candidate. But I had a good connection with him. And I told him, listen, on this topic, in the end, we have someone who seems to fit the profile we're looking for better. But on the other hand, I can offer you something a little more challenging. So I had offered him another topic on something else, but he didn't like it. So I told him, listen, I think that for everything related to transit detection, there are things to explore with artificial intelligence. But to be clear, I don't know anything about it. All right? I guess you don't either, based on what we've discussed. So working on that means I'll be there to talk with you whenever there are questions, the issues, things like that. But I'm not the one who will give you the technical know-how you need to move forward. After that, if it works, that's great. If it doesn't work, well, that's fine too. At least we tried together and so on. But it's true that you'll have to learn a bit on your own. And actually, he liked that. And he did this internship, which was a 6-month gap semester internship at an engineering school. And so, indeed, we trained ourselves in artificial intelligence to apply it to transit detection. And so he also explained things to me. He helped me gain some knowledge in the field, and we experimented. We did things together. And then, after that, I continued with other interns, other victims, if I may say so, until I finally had a student who did their thesis on the subject and who finished their thesis. So he moved on to another model, and yes, actually, he showed that it works really, really well. So what's interesting is that the detection part is actually for the future light curves of the Plato mission. So it wasn't an area I was involved in at all. There are other parts of the mission that I'm involved in as part of my own project. There, it was really just for fun, actually, and it still amuses me, by the way. But when we designed, for example, the part of the pipeline for the mission that will detect transits, we asked ourselves the question. So we're talking about something that will soon be 20 years old. But about 15 years ago, we asked ourselves the question, should we look at artificial intelligence aspects or not? And we said, no, it seemed too cumbersome. There's the whole learning part, and then you need real data. So it's something that maybe we can set up when we have the real data, because then we'll be able to train our model. So we had set that aside. And now actually what's happening is that we have simulators, as we call them, that allow us to anticipate what the real data will be. And because I had started working with the simulator data for other aspects, we were able to develop this model, and we know that our simulated data is still quite robust. Later on, we may turn out to be wrong. There may be differences, and we knew that from the start, but it's a first representation. Hugo, my former student, now that he has finished his thesis, what he needs to show is that his model is robust enough so that if we change the simulated data, it can still work well, with a success rate that is actually quite impressive, in fact.
So
there's potential there, and it allows us to achieve. It doesn't take away from human expertise at all. It's not just I take a model and ping, it works. That's not true. You have to, okay. It's another way of working. Sometimes it's a bit faster for practical applications. But it doesn't change the fact that it will take you time to build the model and make sure it's robust and efficient.
all right. That's very interesting, I think, because we see artificial intelligence evolving faster and faster. Also mixing a little bit with science, being used by scientists to explore certain avenues. Some people sometimes imagine that AI will replace the work of scientists as soon as tomorrow. Here, we really see use cases where, in fact, it supports you, but it doesn't replace the work behind it, the preparatory work that comes beforehand, understanding, working things through, and preparing your methods. So there you go. I found that interesting. Yes.
No, you're right. For me, it doesn't replace it. It's just a different way of working. It also helps save time on certain tasks, let's be honest. But in any case, you have to check, you can't skip that. And it can say complete nonsense. Honestly, it can come up with some real nonsense. You can't just trust ChatGPT. I see students who are starting to use it, staying on ChatGPT, maybe others. There are others, well, okay. But we know it because actually they don't check their results and they come up with real nonsense. If you find answers to questions that are written with a different notation, there's no proof shown, or even some results that are wrong, well, in that case, it's clear that in a way that isn't how it should be used. You have to use it wisely. You have to criticize it. You might use it to learn, but always with great caution. I'd say a researcher's defining quality is critical thinking. Questioning ideas, actually, what we've learned, our own results, our own ways of thinking, and so on. So AI can be a tool to save time on certain tasks, to approach studies in a different way, but humans remain central.
We're nearing the end of our interview. Thank you for this extremely interesting conversation.
Thank you for welcoming me and for giving me the opportunity to talk a little about the work I've done with my collaborators, because this research is carried out by large teams.
Thank you very much.
Thank you.